All right, so to introduce the idea of probabilities and how to work with the concept of and with probabilities and the concept of or with probabilities, we're going to deal with a simple deck of cards. So a typical deck of cards has 4 suits, diamonds, hearts, clubs, and spades. And it has an ace, which stands in for a 1, the numbers 2 through 10, and then a jack, queen, and a king. So if you count that up, 1, 2, 3, 4, 5, 10, up for the numbers, plus a jack, a queen, and a king is 13 different cards in each suit. So 13 times 4 is 52 cards in a standard deck. We're going to leave jokers out because that just complicates things. So to start off, I want to know the probability of getting a club, or more appropriately known as the suit of destiny. So if we were to do a probability of getting a club, I would write that this way. The probability of getting clubs is... Now when you do a basic probability, all you're doing is counting the number of ways that happen like this out of the number of ways it could turn up in general. So if you think about clubs, in a standard deck there are 13 clubs, ace through king, and there are 52 cards in a standard deck. So the probability of getting a club should be 13 out of 52. That means that if you took a random deck, shuffled her up, and then cut the cards, and you just kept doing that over and over and over and over again, 13 out of every 52 card cuts should be clubs. Now if you're good with fractions, you might notice that 52 happens to divide by 13, and that reduces to 1 out of 4. Which isn't a surprise, because if you picked an 8, for example, it's either the 8 of hearts, the 8 of diamonds, the 8 of spades, or the 8 of clubs. Only one of those is a club, 1 out of 4. So it's not a coincidence that those two fractions happen to equal each other. Now the next one here, getting a non-face card. Now we could get into a fight whether an ace counts as a face card or not, and if you say that it is, you're wrong. Because you will not find a face on an ace card. So if we go and look, the probability of not a face this is the good part about being the person making the videos. I can make these broad and outrageous claims that an ace is not a face card, and there's nothing you can do about it. So there. So not a face card. So there's the ace, the 2, the 3, the 4, the 5, all the way up to 10. So there are 10 cards that in hearts that are not face cards, and there are 10 diamonds that are not face cards, and there are 10 clubs that are not face cards, and 10 spades that are not face cards, for a total of 40 out of 52 cards. Now both of those numbers divide by 4 as well. That's going to give 10 out of 13. Now that's the number we had out of each suit. 10 cards, the ace through 10, out of the ace through king are not face cards. So we have that. Excellent. So now that we've got that established, I would like to talk about the probability of getting a card that is a club and not a face card. So if I were to write that in my notation here, that would be the probability of a club. The word for and is the intersection symbol. And not a face. Now, I want to think about that. So the cards that are both clubs and not a face club are the ace of clubs, 2 of clubs, 3 of clubs, 4, 5, 6, 7, 8, 9, and 10 of clubs. That's 10 cards out of the standard deck. 10 out of 52. Now that fraction happens to reduce both of these numbers cut in half. That would be 5 out of 26. Now that's fine for something that we know about, something that you can take. You can take a deck of cards and spread them out on the table, and you can count the things that meet both of these criteria. But the real advantage of probabilities, and when you're dealing with statistics in particular, is that if you know the probability of one thing and the probability of another thing, you should be able to calculate the probability of something being both of those quantities. And it doesn't have to be things about suits and face cards. If you knew the probability of someone making more than $100,000 a year and the probability of somebody being born in Bruce County, then you should be able to go through and calculate the number of people who make more than $100,000 and were born in Bruce County based on these numbers. So we're going to just try a calculation and see how it goes. So the way the theory works is that if, and let me underscore this word, A and B are independent events, then the probability of A and B is the probability of A happening multiplied by the probability of B happening. Now that's real general and maybe a little difficult to wrap your brain around. This phrase up here, independent events, means that the two things have nothing to do with each other. So an example of something that might not have anything to do with each other is the probability of being more than 6 feet tall and the probability of liking blue as your favorite color. One assumes, hopefully correctly, that your height above the ground doesn't affect your preference for the color blue. So I should be able to find the probability of 6-footers who like blue by taking the probability of being over 6 feet and multiplying it by the probability of liking blue. An example of something that is not independent would be something like the probability of getting in a car crash and the probability of surviving a car crash. Because you can't have survived a car crash without having been in one. Those two things aren't independent. So when you're doing this particular calculation, you have to ask yourself, are these events unrelated? And if they are, you're good to go. The flip side of that, which is maybe the more interesting one, is that if you do this calculation and the observed probability and your theoretical calculated probability, if they don't match, then that's a sign that two things are in fact connected somehow, even if you don't think they should be. But we're going to get to that shortly. So we're going to try this out with this idea of being a club and not a face card, because we already have an answer for that. So if I were to try and use this formula then, the probability of being a club and not a face should be the probability of getting a club and the probability of it not being a face card. Alright, now the probability of being a club was 1 out of 4. And the probability of not being a face card was 10 out of 13. Now, if you multiply those two things together, because you have excellent fraction skills, numerator times numerator would be 10, and 4 times 13 would be 52. Now, that fraction should be familiar to you because we already wrote it down here. And we got this one by actually laying the cards out on the table and counting which ones actually met those criteria out of the total deck. So, hooray for us. We've just shown that that happens to be true. So trying to do the probability of a card that is a club or a face card, if you start thinking about that, in our notation, the probability of a club, the symbol for or is the union, or non-face. If you think back to the Venn diagram on the other side, that would include all the cards that are clubs. So that's 13 of them. There's 13 clubs in there. And I have to add to that all of the non-face cards that are not clubs. So there's 10 hearts, 10 diamonds, 10 spades. That's 30 cards. Plus the 13 clubs should give me 43 cards out of the 52 that are either clubs or non-face cards. So if I were to try and write this, the probability of A or B, I'm going to start a formula here, and it's going to be wrong. So then we're going to add to it in a second. When I did A and B, I just took the probability of A and added it, or multiplied it to probability of B. This one, I'd like to add them. Probability of A plus the probability of B. And maybe you'll see why this doesn't work in just a second. So in this example here, the probability of it being a club or a non-face card or non-face would be the probability of a club plus the probability of non-face. Well, the probability of getting a club was 1 out of 4. And the probability of a non-face was 10 out of 13. Now, we could do this with fractions. I'm going to flip to decimals just so no one has a heart attack. So 1 out of 4 is 0.25. And 10 out of 13 is 0.769. And if I add those, I get 1.109, or 1.019. That's a 101.9% chance. So round that just for fun. That's a 102% chance. That's wrong. If I were to hand you a deck of cards and say, pick one at random, what's the probability that the card you pick is a club or a non-face card? Well, there's two issues with that. First off, you can't have a 102% chance. It's either 100% or that's it. You can't get an extra card or be extra more than 100% sure it's going to happen. That's not a thing. Unless you're giving 110% in data management, and then that's a good idea. Anyway, so that's the first problem. This number can't add up to more than 100. The second issue is that you might reach into that deck of cards and pull the King of Hearts. Well, the King of Hearts isn't a club, and it's a face card. And I already said there was a more than 100% chance of that not happening. So this is all inconsistent. The problem is that we've overcounted. And how did we manage to do that? Well, the probability of a card being a club included the ace through 10 of clubs. The probability of being a non-face card also included the ace through 10 of clubs. So those cards were counted in this pile and they were counted in this pile. Just like the letters that happen to land in both exaggeration and quasimorphism, there are some that land in both sets. So if you just add them together, then you end up double counting a number of your data points. So I have to correct that here. The issue was that some things fall into this and this. So in order to make the calculation work, I have to remember to take out my double counting of the ones that are in A and B. So if I were to do that, minus the probability of them being clubs and non-face, see, what was the probability of them being a club and a non-face card? Well, I think we calculated that as being a club and a non-face card was 10 out of 52. Which was 5 out of 26. Gross. Now I could subtract that out as a decimal. .192 if I do some rounding. And if I try that again, 0.25, so that's the probability of being a club, plus the probability of being a non-face card, minus the probability of being both, I end up with 0.827. That's an 82.7% chance. Okay, great. When I looked over here in the last example, I happened to find my answer just sitting casually waiting for us to discover it. And so we're going to check this then. What is 43 out of 52? If I do that, 43 divided by 52, I end up with 0.827 if I round. So by adding this little correction in here, where I take out the double counting of things that are both this and that, I'm able to calculate these probabilities for independent events. So the last idea we need to cover here in the basics of the probability operations is called conditional probability. And these probabilities, when you're asked these, they're phrased in a sort of curious way. So I want you to think about pulling a card up out of the deck. And the question I'm going to say to you is that card, I'm going to tell you that it's a non-face card. And now that you know that, I want you to tell me the probability that it's a club. So the way that's phrased is, what is the probability of a card being a club? So you draw it. I look at it. I know that it's a 9. What's the probability that it's a club now that I know it's a non-face card? Now, if we just think about the answer to that before we do any math, if I were to hand you a card and say, this is an 8, so we know that. It's a non-face card. This is an 8. What's the probability of it being a club? Well, it's either the ace of or the 8 of clubs, or diamonds or spades or hearts. So it should be 1 out of 4. That's the answer we should arrive at. So if we can try and bend this calculation and the notation to get 1 out of 4 as our answer, then we will have succeeded. So what is the probability of a card being a club given that it is a non-face card? So the way you write that is the probability of a card being a club given that it's a non-face card. Well, there is a formula for calculating this. The way that you're supposed to arrive at this numerically is to take the probability of it being a club and a non-face card and divide it by the probability that it's a non-face. So when you read these, the probability that it's this, given that, you notice that the non-face went in the denominator here, and the club and non-face went in the top. So if I were to do this, the probability of it being a club and a non-face, so we already worked that out. That was over here, 5 out of 26. And the probability of it being a non-face card was 10 out of 13. Alright, now, you're going to have to get your fraction skills in order to work something like this out. I have a fraction divided by a fraction, so I'm going to write it this way. There's a rule you may have remembered from grade 5 where if you divide by a fraction, you invert and multiply. Well, 5 times 13 is 65, and 26 times 10 is 260. Now if we were to take a calculator and give that a try, 65 divided by 260 is 0.25. Curious. And that happens to be 1 out of 4, which is the answer we'd already arrived at. So this one is a bit tricky to wrap your brain around about what it's asking you exactly. So that phrasing, what is the probability of a card being a club given that it is a non-face card, is we've decided that it is a face card already. So I want to see, I'm going to use this as a tool, in fact, to test whether things are independent. If this is the case, if this and this are independent of each other, do you notice that this probability happened to match exactly the probability that it was a club? So if the probability of it being a club, given that it's a non-face card, happens to be equal to the probability that it's a club, then you've shown that those two things, being a club and being a non-face card, are independent events. They have nothing to do with each other. So I'm going to take this idea and I'm going to write it down as formulas so you have something to look at. And B divided by the probability of B, and if probability of A given B happens to equal the probability of A, then A and B are independent events. And we're going to try that on the next set and the next exercise, and hopefully that will make a little more sense.